Hey everyone, welcome. Today, we're diving into a hidden science that literally powers our world, electrochemistry. It's the magic behind everything from our batteries to the shiny chrome on a car. And trust me, by the end of this, you'll see how it connects some very unexpected things.
All right, so let's just jump right in with a question for you. What on earth does a TV remote have in common with a big slab of pure copper? I know, they seem completely different, right? But the answer connects them both, and it's the key to understanding a huge chunk of modern technology.
Well, the answer to that puzzle is electrochemistry. At its heart, it's the science that acts as a bridge between the world of chemical reactions and the world of electricity. It's all about this awesome interplay, turning chemical reactions into electricity and then flipping it around and using electricity to make chemical reactions happen. And that right there, that's the big idea I really want you to grab onto. Think of electrochemistry less as a single process and more like a busy two-way street for energy. It's not just a one-way trip. Energy can go in both directions, and each direction serves a completely different but equally important purpose. And this slide, it lays it out perfectly. On one side of the street, you have chemical energy turning into electrical energy. That's your TV remote's battery, basically acting like its own little power plant. On the other side, you have electrical energy causing a chemical reaction. That process is called electrolysis, and it's a total powerhouse in industry for making all kinds of essential materials.
Okay, so we get the remote control. But beyond that, why does this two-way street really matter? Well, let me tell you, its impact on our modern world is just huge, absolutely massive.
I mean, seriously, this stuff is everywhere. We use electrochemistry to get super pure metals, to put that shiny protective coating on car parts and tools, that's electroplating. We use it to produce vital industrial chemicals. And get this, looking to the future, it's the science behind fuel cells, one of our biggest bets for a clean energy future.
All right, so we've covered the what and the why, but now let's get into the really cool part, the how. To really get a grip on electrochemistry, we have to understand how electricity actually moves through different stuff.
So, at its most basic level, electric current is just charge on the move. Simple as that. But for that charge to go anywhere, it needs a path, right? A road to travel on. And we call that road a conductor.
But, and this is the big question, is there only one way for that electricity to flow? Is the current zipping through a copper wire the same kind of thing as the current in, say, salt water? The answer is a big, fat no. And that difference? That's what electrochemistry is all about.
And that brings us to the main event, really. We're talking about two fundamentally different ways that electricity can move. It's a showdown, you guys. Electrons versus ions. Tiny, speedy electrons against these bigger, migrating ions. Okay, first up in the ring is the one we all know and love, metallic conduction. This is the electricity flowing through the wires in your house right now. The champions here, the little guys carrying all the charge, are free-floating electrons. The process is actually pretty straightforward. You apply a voltage to a piece of metal, and all its free electrons basically get told, okay, everybody, march this way. That organized flow of electrons is the electric current. And here's the most important part to remember. The wire is just a highway. The metal itself doesn't change at all. The electrons just pass through.
So let's recap metallic conduction. The charge carriers? Electrons. Is there a chemical change? Nope. And it all happens in solid metals. But here's a super interesting, kind of counterintuitive point. If you heat up a metal wire, it actually gets worse at conducting electricity. The atoms start vibrating and basically create a traffic jam for the electrons.
All right, time for our second contender, electrolytic conduction. This is what happens in a liquid, like when you dissolve salt in water. Now the charge isn't carried by those zippy little electrons anymore. It's carried by these much bigger players. Entire charged atoms or molecules we call ions.
So, how does this work? Well, you take something like salt, an electrolyte, and dissolve it. It breaks apart into positive ions, called cations, and negative ions, called anions. Then, when you apply a voltage, it's like a magnet turns on. All the positive cations start moving to the negative terminal, and all the negative anions head for the positive terminal. And that movement, that physical parade of ions from one side to the other, that is the electric current. Okay, let's break down the key features for this one. The charge carriers are ions, and this is a huge difference. Chemical reactions are actually happening when those ions reach their destination. And of course, it all happens in liquids. Now, remember how metals hated heat?
Well, with electrolytes, it's the exact opposite. You heat them up, the ions can move around more freely, and conductivity actually goes up.
Okay, so we've seen our two contenders in action. We've got the electrons in one corner, the ions in the other. So now let's put it all together with the ultimate cheat sheet, a side-by-side comparison that's going to make everything crystal clear.
And you know, the source material for this explainer really flags this part as very important for exams. So hey, if you're studying for something, lean in close, because if you remember just one thing from all this, this should be it.
All right, just look at this table. It makes everything so clear. Who carries the charge? In metallic, it's electrons. In electrolytic, it's ions. Is there a chemical change? For metallic, no way. For electrolytic, absolutely. That's the whole point. What state of matter? Solids for metallic, liquids for electrolytic. That's why we call one an electronic conductor and the other an ionic conductor. It's all right there.
And if you had to tattoo one sentence on your brain to remember all this, it would be this one. Metallic conduction involves flow of electrons, while electrolytic conduction involves migration of ions. That is it. That's the fundamental difference in a nutshell. So I want to leave you with a final thought to chew on. Think about it. The most exciting frontiers in energy technology, we're talking next-gen batteries, super-efficient fuel cells, they're all based on controlling ions. So as we look ahead, maybe the next great energy revolution isn't just about wrangling electrons in a wire, but about becoming true masters of the ion. Something to think about. Thanks so much for tuning in.